Morning students. So today we'll start with the next measurement technique, which is peak reading AC voltmeters. Okay, so see, in some occasions the peak value of AC waveform is it's very important. This is necessary in order to obtain maximum dielectric strength of the insulating solids. Okay, so when the waveform is not sinusoidal, in that case, RMS value of the voltage is multiplied by root 2, which is not correct. Okay, so hence a separate peak value measuring instrument is required. Okay, so here we'll go through the peak reading AC voltmeter circuits, which consists of there are two types here. Again, a series capacitor peak voltmeter and another peak voltmeters with potential dividers. So first we'll see the series capacitor peak voltmeter. Okay, so when a capacitor is connected to a sinusoidal voltage source, the charging current can be given as I naught equals to V dt integration over time 0 to t, right, which can be rewritten as j omega c into V. Okay, where our V, capital V, is the RMS value of the voltage, and omega, which we are seeing here, is the angular frequency. Okay, now if a half wave rectifier is used, the arithmetic mean of the rectifier current is proportional to the peak value of AC voltmeter, AC voltage. So you can see here I have shown the schematic arrangement. Okay, so the DC meter reading is proportional, right? Whatever you get here, the DC meter reading is proportional to the peak value Vm. Okay, so Vm we give as, Vm is what? Vm would be equal to 1 by 2 pi Fc. Okay, right? So this method, what I have shown you, this is also called as Chubb-Fortisk method for peak voltage measurement. Okay, this is the Chubb-Fortisk method for peak voltage measurement. Now you can see here the diode D1. Okay, let me take back you to this figure. Okay, so here there is a diode D1. So this diode D1 is used to rectify the AC current in 1/2 cycle. While you can see here one more, see, this is a half wave rectifier circuit. Okay, so you know the operation. So for positive half cycle D1 conducts, negative half cycle D2 conducts. Okay, so see here diode D1 is used to rectify AC only in 1/2 cycle, while D2 bypasses in the other half cycle. Okay, so this arrangement is suitable, whatever we have shown you is suitable only for positive or negative half cycles. Okay, and is valid only when both the half cycles are symmetrical and equal. Okay, this is important, it has to be symmetrical and equal. Okay, however, this method is not suitable when the voltage waveform is not sinusoidal but it contains more than one peak, okay, or positive maximum or negative maximum as shown in the figure. Okay, here you can see here it is having more than one peak. Here it is having peak, here it's having peak here, right? See, so many peaks it is having. So in this case we cannot go for this type of measurement, right? Now the charging current through the capacitor changes its polarity within 1/2 cycle itself. Okay, here you can see. Okay, so the charging current through the capacitor. Where is the, here, see, here is the capacitor. We have a capacitor here, right? So the charging current, it is said here, the charging current through the capacitor changes its polarity with one of the half cycles, and the current, okay, and the current within that period subtracts from the net current. Okay, so you can see here, right? You can see the shaded areas. Okay, the shaded areas, these areas. Let me clear the slide. Okay, so you can see the shaded areas here. Okay, so this gives the reverse current in one half of the cycles. Okay, so see, the current within that period subtracts from the net current. Okay, hence the reading of the meter will be less and not proportional to Vm. Okay, as the current flowing through the intervals T1 minus T2, okay, you can see here T1 and T2 are here. Okay, so as the current flowing during the intervals T1 minus T2 etc. will not be included in the mean value. Okay, will not be included in the mean value. Now see, this was we were talking about the first false maxima. Okay, next, the second or the next false maxima is easily spotted out by observing the waveform of the charging current on an oscilloscope. Okay, you can see it on an oscilloscope, right? So under normal conditions with AC testing, such waveforms do not occur. And as such do not give rise to errors. Okay, under normal conditions with AC testing we do not get any false maximum, we get a good sine wave. Okay, so these do not give rise to such errors. So, but what happens, pre-discharge currents, okay, within the test circuits, test circuits will have some pre-discharge currents. So pre-discharge currents within the test circuits cause very short duration voltage drops, which can include the errors. Okay, so this problem can be overcome by using a resistance R in series with the capacitance C, such that the CR, okay, time CR is too much less than 1 by omega for 1 by 50 Hertz application. Okay, so this error which we are talking, okay, due to that resistance is given as delta V divided by V equals to V minus Vm, which can be rewritten as 1 minus 1 divided by 1 plus omega square C square R square. Okay, where V is the actual value and Vm is the measured value. Okay, now the different sources that contribute to the error, okay, are first one, the effective value of the capacitance, being different from the measured value of C. Okay, the capacitance you can see here, if the effective value of this capacitance is not taken properly, okay, the effective value of capacitance, if it is different from what we have measured, okay, that may contribute to error. Next is imperfect rectifiers which allow small reverse currents. Third one is non-sinusoidal voltage waveforms, if it has more than one peak, or I told you false maxima for every half cycle, and the deviation of the frequency from that of the value used for calibration. Okay, if in these cases we encounter the error. Okay, now above this, right, see this, as such this method in its basic form is not suitable for the waveforms what I told with more than one peak in each half cycle. Okay, so we can go for a digital peak reading meter for the voltage measurement. Okay, so this is how a digital peak meter looks like. Okay, so see, instead of directly measuring the rectified charging current, a proportional analog voltage signal is derived, which is then converted into a proportional mean frequency FM. Okay, so earlier in series peak voltmeters, what we had done, Im is proportional to voltage, okay, charging current. But here what we are doing, instead of directly measuring the rectified charging current, a proportional analog voltage is derived, which is then converted into a proportional mean frequency FM. Now the frequency ratio FM by F is measured with a gate controlled circuit. Okay, let me take you to this. Okay, gate controlled circuit. Okay, where your see, block diagram 2 is your gate circuit. Okay, which is controlled by AC power frequency F. Okay, which is, see, this is controlled by AC power frequency F, and a counter that opens for an adjustable number of periods, which would be, that period we can define as delta T, okay, which would be equal to P by F. Okay, you can see here, okay, which can be equal to P by F. So this interval, during this interval, the number of impulses counted N can be given as N is equal to Fm into delta T, where delta T is what? P divided by F. So I have written P into Fm by F, which is equal to 2P C Vm A into R. Okay, where P is a constant of the instrument and A represents the conversion factor of AC to DC converter. Okay, so A, right, can be written as Fm. See, if I want to write A, since it's a conversion factor, right, A can be written as Fm divided by R into Im. Okay, where Im would be rectified current through a resistance R, which you can see here. Okay, see, this part is actually a rectifier. Okay, so this type of instruments, okay, conventional instrument of this type, okay, these are available with very much less error even giving you less than 2%. Okay, so this is all about series reading peak voltmeter, okay, series capacitor peak voltmeter. So next video will be on the peak voltmeters with potential divider. Okay, thank you.